Ladies and gentlemen, class recording started, as you can see. You ready? Good, good. Settling in. On Friday, we talked about the idea of conservation of energy. And we said that when something is conserved, that means that it's when a quantity is conserved, it remains constant. And we said that energy is one of those things that is conserved, but when we talk about conserving energy, we have to talk about total energy. And not just the kinetic, potential, elastic, and potential gravitational that we deal with a lot of the times. We also have to deal with things like chemical and heat and all those things that are a lot harder to measure. So what we find out is that under certain conditions, we can see the conservation of mechanical energy. We said that that only applies when conservative forces are acting on an object. The main conservative force that we deal with most often is gravity. But that when gravity is the only force acting on the object, we get rid of all those other forces, we are going to see the mechanical energy be conserved. Earlier in this presentation, we talked about what mechanical energy was. Mechanical energy is a combination of three different kinds of energy: kinetic, gravitational potential, and elastic potential. We may see an individual change in kinetic energy from beginning to end, or potential energy from beginning to end, but if we look at the sum of those, we should see, when gravity is the only force acting on the object, that sum remain the same. And we showed this example of this lady falling out of the building, right? That if we watch her kinetic energy, right, her kinetic energy keeps increasing because her speed increases as she falls because of gravity. But there is a corresponding decrease in the amount of potential energy that we see, because as she falls, yes, she's getting faster, but her height is getting lower, so kinetic energy is increasing as potential energy is decreasing. Good there? But we said that only applies, right, when conservative forces are acting on that object, or gravity, to be more specific. So let's look at the last problem on the back page of this packet about this snowboarder. First, I'm going to take this picture and put it on a separate page, because we're going to need a little bit more space than is there to write. And then I'm going to cover this up real quick. None of this is important to you guys, but just so you know what I'm doing. Let's cover this up. Okay. So it says, a 75-kilogram snowboarder coasts on a smooth track that rises from one level to another. If the snowboarder's initial speed is 4 meters per second, as is in case 1 below, the snowboarder just makes it to the upper level and comes to rest. With a slightly greater initial speed of 5 meters per second, as is in case 2, right, that's the second picture that you guys have there. Now that initial speed is 5 meters per second. Oh, too far. It says the snowboarder is still moving to the right when it gets to the top of the hill. So in the first case, he's going just fast enough that when he gets here, he stops. But in the second case, when he's going a little further, when he gets to the top of the hill, he continues moving. So it says, what is the snowboarder's final speed in case 2? Ultimately, this is what we're looking for. That's what the question is asking us for. But knowing that this guy is going to be on top of the hill, or the snowboarder is going to be on top of the hill, we need to know a little something about this hill, especially how tall it is, because we need to know how much potential energy he's going to have at the top of that hill. So going back to case 1, we're going to use case 1 to find this height, and then use this height for case 2. So for part 1 right here, we want to know how high this hill is. So we're going to be looking for a height. Specifically, which height? When does that occur? What part of the problem are we talking about? The end, right? So that's going to be a final. Things they gave us. in this problem to help us get where we need to get to? What kind of information we got in here? Okay, so we definitely got the mass, right? 75 kilogram snowboarder. That's going to give us the mass of this object. What else?
Velocity.
Okay, which velocity? Somebody did it. Anybody?
Initial.
Okay. So it tells us initial speed, right? 4 meters per second. What else does it tell us about the motion of this object? Comes to rest, right? When? At the end, right? So if it comes to rest, that's going to give us another piece of information, right?
Yep.
The final, right?
Yeah.
Okay. Now, another piece of information in here that they didn't specifically give us, right? We want to know how high this hill is. Where are we measuring that from? The bottom. And the bottom is sort of marked for us, right? With this dotted line. Where does this guy start on the picture? Right? He starts at H initial, but in this case, what is H initial going to be?
0.
Okay, starting at the bottom of the hill, that's going to be 0, 2. Good with that?
Yeah.
All right, one piece of important information that isn't necessarily a number, but is important to getting us to where we need to get to. The fact that this is a smooth track, right? Smooth track is their way of saying no friction. And if there is no friction acting on this object, what's the only force that is going to be affecting his motion? Gravity. And if gravity is the only force, right, we said gravity is a conservative force, and when there's only conservative forces, mechanical energy is conserved. Mathematically, that looks like this. MEI equals MEF, right? The initial mechanical energy equals the final mechanical energy. That's what conservation of mechanical energy means, right? Okay. Also, remember, we talked about that mechanical energy is a combination of several different types of energy, right? What are the 3 types of energy that we consider mechanical energy?
Kinetic energy.
Kinetic energy is one of them. And
Potential
potential
energy.
gravitational potential energy and
Elast.
elastic potential energy. So, those 3 up on the board, right? Like, or on the wall over there, right? The 3 signs, yeah, right? There's a reason why these 3 are up there, right? Yeah. So,
Nice.
Oh.
all right, yeah, those 3 up there.
Good
So,
to know.
there's a reason why I picked those 3. So, all right. Oh, Joe's gonna come back and he's gonna mess up our whole thing. All right. So when we're talking about mechanical energy, right? It's a combination. So KEI plus PEGI plus PEEI, right? The combination of those 3 at the beginning has to equal KEF plus PEGF plus PEEF. These 2 equations are the same. Bottom one's more detailed than the top. Now, the next part, you might not have to show me all of this when you're doing your problem. If you see this faster than the way I'm doing it now, fine, just do it, all right? But to make sure that we understand where we're going here, we can make this equation a lot easier to handle right off the bat if we understand the things that influence these kinds of energy. For example, elastic potential energy comes from things being stretched out or scrunched together, right? We talked about that that's where that elastic energy comes from, like rubber band or bungee cord or trampoline or whatever it is. Is anything being stretched or compressed as this guy goes up the hill? No. So right away we can get rid of 2 things in this equation, right? We don't have to worry about elastic energy initial, and we don't have to worry about elastic energy final. They're both going to be 0. All right, then, based on some other things that we know about these kinds of energy, what did it tell us that happens to this guy up at the top of the hill? Stops, right? So, what is that going to do to KE final?
Zero.
If he's not moving, doesn't have any kinetic energy. What does potential energy depend on?
Stop. It's like how much potential it has.
We said potential energy depends on three factors, right?
Height.
Mass, gravity, and height, right?
So
Good.
if he's at zero, would he not have any height?
If he's at zero, he doesn't have any height. And if he doesn't have any height, Sam, what's his potential energy?
Zero.
So what can we get rid of?
And potential energy, gravitational initial.
That one goes away too. And now, this seemingly daunting equation has become pretty simple. KEI equals PEGF. Okay? Now, we've talked about these kinds of energy, right? And, luckily for you, they're up on the wall, right? So, how do we calculate the kinetic energy of something?
1/2 mass.
1/2 mv squared, right? And because we're talking about initial kinetic energy, which velocity do we want?
Initial.
Initial velocity, right? Here, how do we calculate gravitational potential energy?
75.
We already talked about this,
Mm-hmm.
right? What did we just talk about? How do we calculate gravitational potential energy? Again,
As
mass,
yeah.
G, H, right? And here, we want H final, okay? So just like we said, in this problem, yeah, we're looking for H final, so we should know all the other things in that equation. Go ahead, plug them in, see what you get. Again, if you can do it faster than this, if there's some math stuff that you see that makes it easier, go ahead, do it.
Doodly.
Dude. Yes, Mr. Lomber has left, yes.
Might be from Savannah.
That was my surprise walkthrough observation.
Did we do
It
well?
was pretty scary.
It's pretty, so,
Want
you guys,
some
Oh, yeah, I
back
felt
support?
pressure.
you guys were all on task and everything, that's always a good
Yeah.
thing, so.
I was thinking of bringing something up.
I felt stupid when he came in.
I felt stupid.
You feel right.
Yes.
I always like to see like if teachers act different or not.
And did I?
No.
You didn't really change it all.
I feel like you got a louder voice. That's the only thing I
Well,
know.
a lot of times with that too, when
You
I'm,
did for the
when I'm
recording.
recording, I talk loud
Oh,
anyway
okay.
too. And especially if I walk over here, I want to
Yeah,
make
I-
sure that I got that, so.
That's-
All right, are we good with this? Questions
Yeah.
on that? All right, yes, Morgan?
So, for the left side I got 600,
Yep,
and then for the right I got 75 times 9.81, and I just divided.
yeah, that'll get you each up. So, before we go on to the next part, a little bit of perspective, right? That means the hill that he's going up is 0.82 meters, which would take him to about here. That's quite a hill. Wow.
Is it
So-
4 meters per second? Like kind of fast.
It's not, I mean, it's not real fast.
But it's not slow.
It's not slow. Yeah, I say the picture, according to that picture, if that hill is 0.82 meters,
Well, I guess
he's about 0.3 meters, so, you know. Anyway.
Yeah, that's why I was
He's
like,
a regular Sean White. It is 0.82 meters.
Use that joke second period.
Yeah, I did. So, you know what else I used it? 4, 5, 4, 5. And I used it 6, 7.
I bet you used those last year too.
You probably, actually, no, it's the first year we've done this problem, so.
Did you use the P joke? Did he tell you guys the P joke?
Oh, yeah. That's more of a.
The P. It's
So-
like.
That's more of a
No,
that's more of a self-survival kind of one.
So
you know?
by the time you get to 12th period, it's just like a,
yeah, pretty
like
much.
you don't even
That's
think
why
about
another
it.
another reason
We're just
why
an
you guys get
unoriginal.
recorded all the time is because I've practiced this 3 times already,
Oh.
and so now all my jokes, my timing is down, and I'm like,
Can
man,
you send Lobber the recording?
I should be like, hey man, let me take a look. So So,
There
Yeah,
could be
all
some
this is being
comments on
recorded
that.
right now.
absolutely, it is, yes.
Absolutely.
I warned you at the beginning, right? So, class recording has
What's going on
started.
right now?
So, yeah,
Oh,
watch your language.
Where's the D?
that's Buster's problem.
Very. Oh, well, I thought he called that perfectly.
All right.
Yeah, where is he?
I say it. I don't know. There were like 3 buses, and I don't know if all 3 buses came back yet, or if one of them was behind the other ones or whatever. But so I know you're all concerned, but
I know I was. I text Joe like, we're already sitting on a field trip.
here, let's finish this one up. So, in case 2, this is actually what the question was asking us about, right? It says here that in the second case, he comes into this hill going faster than he was the first time. So he's going 4 meters per second the first time. This time he's going 5 meters per second. It says in the problem now when he gets to the top, he's going to keep going. So this problem is ultimately asking us for V final, right? How fast will he be going when he gets to the top of the hill? Couple of things are not going to change. What's going to stay the same from part 1 to part 2?
Math.
Mass isn't going to change. The mass is still 75 kilograms.
Acceleration. 9.81.
That's true. We don't need to write that down just yet. Then.
Okay.
What else stays the same? Where does he start in this problem?
0.
His initial height is still going to be 0. But then a couple of things are different, right? It told us in the problem that his initial velocity is 5. And we learned in the first part that he ends up 0.82 meters above the ground. Good there? All right. Again, because gravity is the only thing acting on him, right? He's waiting for me to come ask any questions.
Oh.
I'll get you guys started on this, and I'll go talk to him real quick.
Okay.
All right, because gravity is still the only thing acting on it, right? MEI equals MEF. And we just talked about that this gets broken up. Again, you don't have to show me this every time necessarily, but if it helps, go like this, right? That's what that means. Now, examining the different parts of this problem. Again, we can make this a little shorter just by knowing some of the things about the nature of these energies. Like I said, you don't have to show me this every single time. If you see it without showing me this, that's okay. First, anything stretched or compressed. So these 2 go away. Said that he's still starting at what height? 0. So that's going to make his initial gravitational potential energy what?
0.
That goes away too. But unlike the last problem, he's still moving at the top of this hill, right? So we can't get rid of kinetic energy in that part. He's still above the ground, so he has gravitational potential. So at the end of this problem, he actually has 2 kinds of energy. He's going to have kinetic energy and gravitational potential. Okay? Good there? Now it's just a matter of going through, right? 1/2 mv final squared equals 1/2 mv initial squared plus mgh. What we do with h final.
You switch those up right now. Or why is it?
Well, this should be initial, sorry.
Yeah.
And now we're looking for that. Right? So go ahead, plug in things you know, solve for that final velocity, for that final speed.
Elixir storage is upgraded, guys.
What?
Elixir storage.
What's that?
Flashlights.
Are we not gonna know the velocity of the line?
That's what we're looking for, right? So that's our unknown of this stuff.
Okay.
So over here, right? We're at the hog ride.
Yeah.
That's our unknown. So.
Like I said,
And you are
mathematically, doesn't matter. Like if you found some shortcuts, if you can make this process a little bit shorter, cancel some things out or whatever. If you see it, go ahead and do it. If not, just go ahead and plug things in and solve for what you need to solve for.
Yeah.
All of our original numbers, right, have 2 sig digs. If you look up in the problem, all those original numbers have 2 sig digs. So. Same with the unit for velocity.
Unit per second?
All right. Good
That's
here?
corduroys.
Thanks. It's keeping warm.
I
So.
know.
Oh, these are both wearing corduroys.
Yeah.
Those are Kohl's.
I believe these are actually from Kohl's. Wait, no. Like these are Target. So. Wait, I don't remember.
I don't remember.
Where's Sonoma from? I can't remember.
So no, it's
Is that Kohl's?
Yeah, it's
Okay,
Kohl's thing.
Kohl's it is. So.
Wait.
I also have a pair of Dockers
Dockers?
corduroys too. So.
Nice. Not like pair.
I like
Cords
corduroys.
keep you warm.
Cords are so.
I used to
awesome.
have a
They're fun to
corduroy
walk in too,
jacket,
'cause then you
actually.
like rub your thighs.
Yeah,
together.
that's always fun.
I saved up my money in like first grade for a
Corduroy jacket,
Yeah,
man.
I never
It's-
got it.
Yeah,
I
that's
could
it.
never save
When
my
I was
money.
when I was in grade school, so badly wanted a jean jacket, so badly. Never got one though. In retrospect,
Hey, you
I
can
think
get
it was
one
probably a
now.
good idea. So.
Now you could go get a jean
Yeah.
jacket. They're everywhere.
Jamie, do you remember this SpongeBob where he gets the pickles and he's like so tiny squeaky?
Or the one where
SpongeBob is
Patrick
a-
tries putting on the
SpongeBob
lid.
is a terrible
He's
show.
like,
And then
he's like they're, what is he say?
horribly cries.
All right. So, one thing to wrap up this discussion. At the beginning of the hill, right? A seemingly small change in this velocity, right? Went from 4 to 5. But remember, kinetic energy depends on mass, but it also depends on velocity squared, right? So even this relatively small change in speed results in still a pretty good speed at the top of the hill. Right? It doesn't seem like we changed the bottom all that much, but it went from stopping at the top of the hill to still going 3 meters per second, only by going from 4 to 5. So we see that changing of the velocity influences the kinetic energy quite a bit. So a small change in velocity can still have a somewhat large change or a large effect on the kinetic energy. Good there? All right. So let's wrap this up and let's transition here to the last section of this unit dealing with power. And we're going to start this discussion on this picture of these people going up the stairs. So two instances going up the stairs, right? If we look at the energy in both cases, so let's say to make our lives easy, we're going to assume both of these people have the same mass. And one person walks up the stairs, one person runs up the stairs. They both start down at the bottom, they both end up this high off the ground. So just like we did before, we're going to see an increase in energy. Specifically, what kind of energy in this situation? Well, kinetic for a little while, right? But if you look at beginning to end, bottom of the stairs to top of the stairs, we're going to see an increase in what?
Potential.
Gravitational potential, right? While they're moving, they will have kinetic, but if we look at beginning and end, we're going to see an increase in potential, right? Does that make sense? So here we'd probably call this height equals 0, and then here, this is some height. We don't know exactly what it is, but we'll call it h. And that being the case, when both of these people are at the bottom, what can we say about their potential energy?
0.
If they start at the 0 height, they're both going to start with 0 potential energy. And then they both end up the same height off the ground, right? So what could we then say about their gravitational potential energies?
So the same.
They're going to be the same if we assume they have the same mass. So PEG for the walker is going to be the same as PEG for the runner. There is a change in energy. What causes a change in energy, or what do we need in order for the energy of an object to change? We have to do what? Work, right? If we see the same increase in energy in both cases, what could we say about the work that is done in both cases? It's going to be equal to. So the work, and I should use a different color there. So the work done by the walker is equal to the work done by the runner, because their energy increases by the same amount. But if we look at analyzing this situation, right, there's definitely a difference in the person walking up the steps versus the person running up the steps. Now, granted, if you're that winded after you run up the steps one time, you might have to, maybe mix in a little cardio, but, right,
Yeah,
there's
that's not that
definitely a
many stairs.
difference.
Is that right?
That's not that many stairs.
No,
for him to be
and
like dying.
he's like bent over and
I went tobogganing this weekend and there were so many stairs.
yeah, that's the thing about tobogganing,
When I tried to run up one
not,
with
Sam,
all my gear and
Sam,
stuff,
this is a good lesson for you then,
Yeah.
right? So Sam runs up the steps, right? And what happened when he ran up the steps, Sam?
I got tired.
Super tired, right?
Yeah, I had to
But
stop.
when you walked up the
Like
steps,
halfway.
though, right?
I still got tired.
Still got tired, but not as tired, right?
Still dying.
So there has to be some other factor than just how high up you go. And that factor that we look at is power. So like it says here, power is a measure of how quickly work is done.
Is this one where, are we doing a lab about running upstairs?
We could, but I haven't scheduled us to do that.
yeah,
so.
let's do it.
I want to see how many horsepowers I see. Isn't that what it is? Like, that's the horsepower
We
lab?
can't figure that out. So maybe we'll do that
We should
tomorrow
do
instead of
that.
the lab I have scheduled.
Yeah.
I'll bring my running shoes. I already beat it.
Power is defined as the amount of work done in a given amount of time. So power is equal to W divided by T. How much work did we do versus how much time it took to do that work? Key point. Right? The faster work is done, the greater the power. So when we talk about getting tired, quote unquote, we can't just look at how much work is done. We also have to look at the rate at which work is done. So in this case here, walking up the steps versus running up the steps, we've established that they both do the same amount of work. But will the power be the same? No. Which power is going to be bigger? Running power, so power of the runner is greater than the power of the walker, because they accomplish the same amount of work in a shorter amount of time. And that's something we have to look at when analyzing a situation. Power is measured in a unit called the watts. Most of you are probably familiar with watts from the idea of a light bulb and how bright a light bulb is. But wattage, it does not relate to how bright something is. It relates to how much energy is being transferred. A watt is defined as 1 joule per second. Joule being the unit for energy, second being the unit for time. Another unit that we use for for power, remember, converting energy from one form into another, how quickly does that happen, is the horsepower. 1 horsepower is equal to 746 watts. It's not a nice round calculation because horsepower is an English unit and watts is a SI unit, so it's not a nice even conversion, but that's what it is. Okay, both measuring the same thing: how much energy is converted per second. Good there? All right, so to illustrate that point, let's do this problem here. Problem number 616, passing fancy. It says, to pass a slow-moving truck, a driver has to accelerate his fancy car from 13.4 meters per second to 17.9 meters per second. So from 30 miles per hour to 40 miles per hour. 3 seconds. What is the minimum power required to do this? So first, this question is asking us for what? Power, right? What is the minimum power? And we just learned that if you want to calculate the power for something, you need to know 2 things, right? What do you need to know?
Work.
Work and time, right? So work and time. So this is one of those things where yes, it's asking you for power, but you need to know 2 things if you're going to calculate the power. Did they give us either one of those?
Yes.
They gave us one in the problem, right? So there's 3 seconds. They didn't give us the work, at least not straight off, but they gave us a couple other things, right? They gave us the mass as 1,300 kilograms, if we take that from scientific notation into decimal notation. And then from 13.4 to 17.9, they actually gave us what? It's not just velocity, it's actually
Acceleration.
not quite.
Miles.
It's how many velocities?
VF and VI.
VF and VI, right? If it says from this to this,
Oh.
right? VI is going to be 13.4, and then VF is going to be 17.9, right? It's saying from this to this, okay? All right. So far in this unit, we've talked about 2 ways that we can calculate the amount of work that is done. What's one way that we can calculate the amount of work that's done?
Change in kinetic energy.
Okay, we've talked about that the amount of work that we do on an object is equal to the change in the kinetic energy. Sam, what do we call that? Do you remember?
No, it's the work, energy, theorem.
That's the work energy theorem, right? That the amount of work we do on an object is equal to the change in the energy, right? We said there's another way that we can calculate the amount of work that's done. Do we remember how to calculate? The other way to calculate the amount of work that's done. We need to know 2 things, right? What's another way? Right? FD or F cosine theta times D, right? What's going to be the better choice for us in this problem? Okay? We don't have a force and we don't have a distance, so that's really not going to work, right? So we're going to have to go with looking at the change in the kinetic energy. So work equals delta KE, but to find delta something, right, we need to know what?
Initial and
Initial and final, right? So KE final minus KE initial. We know that the kinetic energy of an object influenced by 2 factors, right? And we have enough information here now to calculate the amount of work that is done. So let's calculate the amount of, let's sub in things we know, plug in things we know, find out how much work is done in this situation. Right, we've encountered another problem here where it's asking us to find work, but they didn't really give us force and distance. We can find the amount of work that's done by looking at the change in an object's kinetic energy. let's keep it like this because we're not done with this problem, right? We're gonna use that number to do something else.
Yeah, I'm just kidding.
All right, so we get this, right? That's how much work is done, 91,552.5. But that's not what the question asked us for, right? The question asked us for power. We just learned a little while ago that power is defined as what?
Work over time.
Work over time. So 91552.5 joules over 3 seconds. And that gives us, it's like 30,000 something, right?
30,517.5.
So 30,517.5 units wise, joules on the top, seconds on the bottom. Okay, so if we look at our problem, 3 sig digs are in the measurements that they gave us originally. Joules per second, Margot, we said that was what?
Watt.
That's going to be watts. Okay. All right. As far as the test goes, power is going to be pretty minimal as far as the test is concerned. It'll be on there a little bit, but not a whole lot, seeing as how we just spent about 20 minutes covering it, and that was about it. So tomorrow we'll do practical lab. Maybe we'll do the horsepower lab and see how that goes.
Okay, so
The rest of the week are reviews.
No, just doing review stuff and preparing for the test. Okay.
What room
So,
is the bottom?
all right.